Hi, in this video we will do some new examples of applying integration by parts, and we will notice that sometimes some functions, when you apply integration by parts, maybe twice or several times, um, you get a function plus a multiple of the original function. And I'll show you how in these cases you find what is the integral of fx dx. That I will call double trick. Okay? So you do several times integration by parts. You start with one integral and then end up with a function plus multiple of the same integral. Okay, let's see this in this example, e to the power x sine x. We already seen examples that polynomial times e to the power x or polynomial times sine x. In those cases, you take u to be that polynomial. In this case, well, you can either take sine x to be u or e to the power x to be u. Well, I'm just choosing to use that one, sine x to be u. So dv will be e to the power x dx. In this specific case, you can do both choices. So I have u, which is sine x, dv, which is e to the power x dx. Then I differentiate the first one to find du, which is cosine x dx, and then integrate the second one time to find v. Now I can apply IBP, e to the power x sine x dx. This would give me uv, so e to the power x sine x, the order doesn't matter here, minus integral of v du. So e to the power, let me just write it like that, cosine x, I can do e to the power x cosine x dx. And you see that we are very close to what we had at the beginning, but this time we have cosine x. Anyhow, that integral, again, I cannot do that integral unless I do another IBP, well, hoping that that will solve my problem. So second IBP comes in. In the second IBP, I do the same thing. So in the first one, I take u to be sine x. Here I will take the cosine x to be u. dv is e to the power x dx. As a result, du is going to be minus sine. Derivative of cosine x is minus sine x. And v is going to be integral of e to the power x dx, which is just e to the power x. So now I apply integration by parts for the second one, for second time. So u dv, here's e to the power x cosine x, minus integral of v du, e to the power x minus sine x dx. Okay, let me simplify everything. So this is e to the power x sine x dx equals, the first term is e to the power x sine x. The second one, I should multiply this minus signs in. So this is e to the power x cosine x. And then there is this minus sign also inside. There are three minus, 1, 2, 3 minuses. So that will give me minus integral of e to the power x sine x. Now, look carefully, look closely what we have here. So we are looking for this guy, and we found that that is equal to a function minus that itself. Now, it's like I have an equation for a function. That function is integral of e to the power x. X, an unknown, say y, is equal to something, some function here. minus y itself. How do I solve that? How do I find y? Well, take it to the other side. There will be two of those guys. So 2 integral of e to the power x sine x dx equals to e to the power x sine x minus e to the power x cosine x. Now, well, the only thing we need to do is divide this one, this coefficient to the left hand side. Integral of e to the power x sine x, that was what we were looking for, is equal to half of e to the power x sine x minus e to the power x cosine x. And that, well, let me just put plus c there just to have that plus c that always we look for. So this way we found integral of e to the power x sine x. The trick that we did right now here, apply IBT twice, and then you go back to the original function, original integral, and then solve it for that. We will call it double IBP trick. I have actually another example. I will do a little bit fast this one. So here I have integral cosine of ln x dx. So here I'll take this whole thing to be my u, that there's only one thing there, and the rest, which is dx, as my dv. So IBP here is u is cosine of ln x, and dv is just dx. As a result, du is going to be, so here you have to apply chain rule. This will be derivative of ln x, which is 1 over x, times derivative of cosine x, which is minus sine, but plug in ln x in that. That's chain rule. And then v you can find by integrating dv, which will give me just x. So my IBP will be cosine of ln x dx equals to u times v. So here is x times cosine of ln x minus integral of v du. So x times negative 1 over x sine of ln x dx. Yes, there's another bracket there. But inside this guy, you see that this cancels with that. I can put that minus sign outside, and this whole thing is going to be plus integral of sine of ln x dx. Now we can apply IBP another time. So again, I'll take u to be sine of ln x, dv to be dx, du is going to be 1 over x cosine of ln x, and v is going to be just x itself. So applying the integration by parts another time, ln x plus, okay, so vu x times sine of ln x minus integral of, so this is a bigger bracket, integral of v du. So x times 1 over x cosine of ln x dx. And you see that that x and that x cancel out. And if I rewrite my computations again, the left hand side was this, equals to x cosine of ln x plus x sine of ln x minus integral of cosine of ln x dx. The same story comes here. I started looking for integral of cosine ln x. After doing twice IBP, I got a function minus the same integral. Now, if I take this one to the left-hand side, I'll get 2 of integral of cosine of ln x dx equals to x cosine of ln x plus x sine of ln x. And then just get rid of that 2. So integral of cosine ln x dx is equal to x over 2. I factor out that cosine of ln x plus sine of ln x. So this way we apply the double IBP trick, and we found the integral of cosine ln x. Integral of sine ln x will go to the same way, and so on. Okay, so this was the trick, and you see it needs a little bit more than just applying IBPs. That then you have to see that by solving an equation for the given integral, you can find the value of that integral.